Hi guys, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. This time we're going to look at simplifying a distributed load. So let's have a look at the problem. So we have a beam with a distributed load that has on the left-hand side a uniformly distributed load of 2 kilonewtons per meter. And then on the right-hand side, a linearly varying distributed load that goes from the 2 kilonewtons per meter up to 4 kilonewtons per meter at the right hand end here. And we want to replace this distributed load with an equivalent resultant force and then specify the location on the beam measured from A where that equivalent resultant force needs to be located. So if we just go to my next page, and I've just repeated the question there for reference, and our solution. So we've got just a simple distribution or simple shape for the distributed load. We've got a rectangle on the left-hand side, another rectangle on the right-hand side with a triangle sitting on top. So we can just use our simple shapes and the geometric properties of simple shapes that you'll find in tables in textbooks. So we've got firstly a distributed load or uniformly distributed load, a rectangle, and then one linearly varying load. So what we're going to do is to split this up into one rectangle like this for the uniformly distributed load, and sitting on top of that we'll have a triangle that we can use to evaluate the linearly varying load. All right, so let's clear that away. Draw our beam. So you should get used to drawing your own diagrams, not just putting answers on the pictures that are given to you. It helps you develop your drawing skills. And in practice, you've got to come up with your own drawings in the first place. Generally, you don't have someone else giving you the drawings. Firstly, we've got our uniformly distributed load here, all the way across the beam, and then that has a magnitude of 2 kilonewtons per meter, and then sitting on top of that from halfway is the little triangular area which goes up to 4 kilonewtons per meter, so 2 plus 2 here gives us that. And firstly we'll work out the equivalent load for the uniformly distributed load, or the equivalent single force for the uniformly distributed load, and we know that the force will pass through the centroid of the shape. So the centroid of a rectangle is just at its geometric center, so we can put that one in easily enough, and its magnitude will be the magnitude of the distributed load, so 2 kilonewtons per meter times the length over which it acts, which is 3 plus 3, 6. So 2 times 6 is 12 for that resultant force. And then for the triangle, the centroid of the triangle, which is where the resultant force will act, is, if we take this vertical side here as the base, the centroid will be 1/3 of the length here away from the base. Okay, so it's got a length here of 3 meters, so that distance there is 1 meter. All right, and its magnitude is the area of under the loading curve, so the area of the triangle. Its magnitude here is, or the length of this side is 2 kilonewtons per meter, the length of this side is 3, and the area of a triangle is half the height times the base, so a half 2 times 3 gives us that, so this will be a magnitude of 3 kilonewtons. So we can put that into an equation. So the resultant force is just the sum of all of the forces, defining downwards as positive, or assuming downwards as positive in this case. So we have 2 times 6, which we discussed, and a half times 2 times 3 gives us a total resultant force of 15 kilonewtons. All right, so now we have done that, we can redraw our beam and place our equivalent single force, but now we need to position it along the beam somewhere. Okay, so the way we do that is to put it arbitrarily somewhere that we think it might be, and then define that position with a variable d that we can solve for, and then we need to make sure that the moment effect of this single resultant force is the same as these two single forces and the same as the original distributed load that we had to start with. Okay, so equating moments, we'll have this force times its distance d here that we need to work out, and then the sum of the moment effects of these two forces whose location we do know. Taking clockwise as positive in this case, so we have 15 times d, so that's our resultant force 15 that we calculated, times its distance from point A, perpendicular distance from point A, which is our unknown d, and then on the right-hand side of the equation, we have this force times its perpendicular distance, so 2 times 6 times 3, and the moment effect of the force due to the little triangular load, or the linearly varying load, is 1/2 times 2 times 3 times its perpendicular distance from A, which will be 3 plus 3 minus 1, which is where we get the 5 here from. And now we can just solve for D, simple maths, and we get the location of our single resultant force is 3.4 meters to the right of point A. Okay, so that's the end of the problem. Hopefully that was helpful, and I'll see you in the next video. Bye for now.